Okay, the title of our notes today are the common ion effect. The shift in equilibrium that occurs because of the addition of an ion already involved in an equilibrium reaction is called the common ion effect. We're really not going to learn anything new today. What we're going to do is we are going to take knowledge that we've already mastered, and we're going to apply that knowledge into a brand new context. Calculate the hydrogen. So calculate hydrogen ion concentration and percent dissociation of hydrofluoric acid in a solution containing 1 molar hydrofluoric HF, with a Ka, that's HF, that's hydrofluoric, the Ka of 7.2 times 10 to the minus 4th, and 1 molar sodium chloride. Okay, so what we're going to try to figure out is how much hydrogen ion is in solution and what is the percent dissociation of hydrofluoric acid in a solution that contains both 1 molar hydrofluoric acid and 1 molar sodium chloride. So now we've got a mixture. Okay, so we're getting ever more complex. So we've got a weak acid in that beaker, and we also have a salt in that beaker. Okay, so the first thing we need to do, because this is a mixture of stuff, is we need to figure out, okay, what is in the beaker? In the beaker, right? This is the question we ask. Okay, so what do we have in there, you guys? Well, we've got water. We've always got that. So, water. What else is in that beaker? Hydrofluoric, because it's a weak acid. It's pretty much all associated. And we also have sodium ion. Where's the sodium ion coming from? The sodium chloride salt. And what else do we have in solution? We've got that fluoride ion in solution. Okay, now, what do we mostly have? What are the things in this solution? What are the major species? What are the things? Well, these are the major species. But what's going to affect pH? Okay, so, I'm probably wrong there. Yeah, I am. No, it's an A. Affecting pH? Well, compared to the hydrofluoric, comparing the Kas here, water is not going to be very significant. We have HF. That's going to be. What about the sodium? Oh, it's the cation of a strong base. No effect. But what about the fluoride? Well, it's the conjugate base of this weak acid, HF, so yeah. Okay, so there they are. There's our two that are going to be affecting the pH of the solution. All right, so now let's go ahead and write the dissociation, the HF dissociation in water. So we've got hydrofluoric going to H plus F minus. Now, let's just think about this. The fluoride that's in solution from the salt, what's it going to do to this equilibrium, this dissociation equilibrium? It's going to drive this thing left, isn't it? So the amount of hydrogen ion that would normally dissociate in this hydrofluoric dissociation, it's not going to be that way because we have fluoride in there already from the sodium fluoride that's going to drive this thing left. Well, how much is it going to drive this thing left? So that's what we've got to find out, because where the equilibrium is at, the position of the equilibrium, of course, is going to determine how much hydrogen ion we have in solution. So, we've got a weak acid, we've got to determine hydrogen ion concentration. We have this new component now that we've never tackled. And we need to figure out the hydrogen at equilibrium. So, we need an equilibrium expression for this thing. It's a Ka. Hydrogen and HF. Okay, there's my expression. So let's do a nice diagram. So what's my initial concentration of hydrofluoric acid? One molar. What's my initial concentration of hydrogen ion? 0. What's my initial concentration of fluoride ion? 1 molar. Why is the concentration of fluoride initially 1 molar? Because of the sodium fluoride salt that's in the solution. We're going to lose, we're going to gain, we're going to gain. So we're going to have 1.0 minus x. We're going to have x, and we're going to have 1.0 plus x. Alrighty. Now, what do you think? If we can call this minus x negligible, what about this plus x? Could we call that negligible too, just to make our life better? Yeah. So let's plug into this equilibrium expression. So what is our Ka value? Our Ka is 7.2 times 10 to the minus 4th. And that's equal to nice the way I made these numbers so easy. So what's my value of x? Oh look, it's that. X is equal to 7.2 times 10 to the minus 4. What is the identity of x? Hydrogen ion concentration. Okay, so there it is. There is the hydrogen ion concentration of this 1 molar mixture, or this mixture of 1 molar hydrofluoric along with 1 molar sodium fluoride. So the other part of this problem is we need to figure out the percent dissociation. So let's do it. Percent dissociation, which is also how we figure out whether we were okay to get rid of our x's using the 5% rule. We have got, let me see, going back, 7.2 times 10 to the minus 4 divided by 1.0 times 100 is equal to 0.072%. Well below 5. Sorry, well below 5%. And so that tells us, of course, that number one, it was okay for us to throw out our x's as being negligible. But number two, wow, it's hardly any hydrogen dissociated at all. I mean, what a job that fluoride ion does keeping that hydrofluoric associated. Let's compare, just because, wow, that's just impressive. So here's our percent dissociation. We also calculated our hydrogen ion concentration. Now, let's look. Let's compare. If our solution had only been 1.0 molar HF, so if we've got a 1 molar solution of hydrofluoric and we set up an ice diagram and plug into our equilibrium expression, what we end up getting is a hydrogen ion concentration equal to 2.7 times 10 to the minus second. And in this case, you guys, we actually have a 2.7% dissociation. On the other hand, if we have 1.0 molar HF in a solution also containing 1.0 molar sodium fluoride, our hydrogen ion concentration in this case is going to be 7.2, what we calculated, 7.2 times 10 to the minus 4. Okay, and what is our percent dissociation? It's 0.0722% dissociation. Let's do the pHs of these two solutions. Okay, we've got a pH here. I'm showing pH 1.57. What's our pH over there? And I'm seeing a pH of 3.14. Okay, this is a significant difference in terms of pH. It's about almost 100 times more hydrogen ion in this solution than there is in this solution. Because, again, this common anion is driving this acid dissociation to the left, keeping it so that very little of that hydrogen can dissociate. I wonder if there's contexts in which this kind of thing could be helpful. Having an acid along with its conjugate base, or vice versa.